Late August 1944, Northern France. At Observation Post 4, Flak Regiment 155W takes over before dawn. The shift begins like any other until the duty officer reaches the previous night's interception report. British coastal batteries appear to have destroyed roughly 82% of the V-1s fired toward England. It is an interception rate far beyond anything seen in the campaign. The figure is so far outside expectations that the staff assumes the reporting chain has failed. They rebuild the tables, verify launch totals, and match radar tracks to British gunfire logs along the channel. Every calculation checks out. Nothing in the launch cycle, timing, or tracking explains the number. Field observers along the French coastline have been seeing the same unexplained pattern. V-1s that look steady over friendly territory begin to behave unpredictably the moment they enter the British gun zone. No fighters approach them. No barrage balloons intersect the flight path. Flak bursts detonate nearby, and the missile still breaks up or spirals down as if struck directly. These reports now reach Colonel Max Wachtel, commander of the ground-launched V-1 campaign. Since June, he has followed British performance closely. Early interception rates were low. Gradual increases through July matched expected improvements in British coordination and radar handling. But 82% is not an incremental gain. It represents a fundamental change in the defense environment. A technical review of German equipment follows. Engine output is tested. Gyroscopes are checked for drift. Training shots over friendly territory fly normally. No mechanical fault appears. The missile remains reliable on the German side of the trajectory. That leaves only one variable: the British defenses themselves. Coastal guns, once considered a secondary threat compared to fighters, are now responsible for most V-1 losses. Their sudden jump in accuracy exceeds every model the Luftwaffe has used. German analysts can offer only a vague explanation: an unknown improvement in British anti-aircraft control and fusing. No intact British shells have been recovered. No intelligence report mentions a new device. No German laboratory has a working concept for the kind of fuse that would be required. On paper, the V-1 remains a viable weapon. On the battlefield, its survivability has collapsed. What none of them realized was that the change had nothing to do with the V-1 at all, but with the shells, a compact American fuse, powered by a one-shot sleeping battery that activated the moment the gun fired. Before the interception data began shifting, German planners had strong reason to trust the V-1's performance envelope. The weapon carried an 850-kilogram warhead, pushed forward by an Argus pulsajet running at roughly 640 kilometers per hour. Its speed alone placed it beyond the reach of most defensive methods Britain had available at the start of the campaign. The missile flew low enough to complicate radar tracking but high enough to stay clear of small arms fire. Altitude varied between 600 and 2,700 meters, and the irregular pulse jet rhythm created minor fluctuations that made prediction difficult. Fire control systems require consistency. The V-1 offered very little of it. Interception by fighters demanded aircraft capable of exceeding the missile's speed with room to maneuver. Only a handful of Allied fighters could overtake a V-1 cleanly, and those engagements left pilots operating within blast range of the warhead. As a result, fighter interception never became the primary British option. Anti-aircraft guns faced their own limitations. A V-1 presented a small radar return, a short exposure window, and no fixed climb or descent pattern. Direct hit probability, based on pre-war German and Allied ballistic models, sat well below acceptable levels for consistent defense. A single error in fuse timing or predictor input meant a wasted round. From Berlin's perspective, these constraints defined the V-1 as a statistically resilient weapon. German engineers believed any serious reduction in penetration rates would require a breakthrough that Britain simply could not achieve under wartime pressure. This confidence shaped the V-1 launch plan. A sustained rate of fire, thousands of missiles over several months, was expected to overwhelm British defenses faster than they could adapt. Even moderate hit rates would impose significant civilian and infrastructure costs on London. When the weapon entered service on June 13, 1944, the initial results matched German predictions. The first impact in London demonstrated that the missile could penetrate air defenses with little difficulty. Follow-on strikes reinforced the assumption. Britain would absorb damage while struggling to counter a fast, cheap, unmanned threat. For the German command, the V-1 existed as a simple equation: a low-cost cruise missile, a short flight path, a predictable corridor, a defensive network too rigid to adapt quickly. No one in the V-1 program expected the key variable to change. They never imagined that Britain would field a fuse capable of doing the impossible, turning near misses into consistent kills. When the first V-1 crossed the Channel on June 13, 1944, British crews encountered the weapon under combat conditions rather than through estimates on paper. The missile's approach exposed weaknesses in the defensive network that pre-war planning had not anticipated. Detection occurred late, tracking required constant correction, and available firing windows closed faster than operators were accustomed to. Inside the London early warning grid, radar stations logged the missile's pulsar jet signature for the first time. The uneven thrust created altitude fluctuations that complicated prediction. Plotters struggled to maintain track quality as the missile skimmed the coast at high speed. Fighter squadrons attempted initial interceptions, but performance limits appeared quickly. Pilots needed a perfect combination of altitude, airspeed, and approach geometry. Any misalignment forced them inside the warhead's blast radius, making the engagement risky. Most passes ended without a clean shot. Anti-aircraft batteries faced similar constraints. The V-1's small profile and rapid transit reduced available reaction time to seconds. Fuse settings had to be dialed correctly on the first attempt. A slight timing error pushed the detonation far behind the missile, turning each round into wasted ammunition. Despite these setbacks, British crews adapted as quickly as conditions allowed. Improved communication between radar operators and gun sites reduced delays. Predictor teams learned the missile's rhythm and adjusted their calculations. These refinements produced modest gains, but the improvements remained within the limits of conventional timed fuses. German monitoring stations tracked these developments from across the Channel. Intercept percentages rose slowly but stayed inside the band predicted by ballistic modeling. To German analysts, Britain's response appeared competent but routine, exactly what a well-drilled defense should produce when exposed to a new threat. By the end of June, the V-1 still behaved like a weapon with clear statistical advantage. Penetration rates remained high. The missile's speed and altitude band continued to tax British defenses. Launch crews in northern France saw no reason to alter their procedures. What the German command did not recognize was that Britain's early adjustments were only a temporary bridge. Behind the scenes, planners were preparing a structural overhaul of the gun belt, one designed to eliminate the timing problem entirely. The breakthrough would not come from pilots or gunners, but from a fuse that required no manual setting and no prediction. Through early July, British interception rates rose at a steady, predictable pace. Then the numbers began climbing faster than any training improvement could explain. Coastal observer logs showed the first anomaly. Flak bursts that should have been harmless were now consistently disabling V-1s. The detonation spacing looked tighter, more controlled, and out of line with ordinary timed fuse behavior. British analysts noticed the same issue. Their crews were performing well, but not enough to justify the sudden jump. Nothing in radar drills, predictor adjustments, or gunline coordination matched the new effectiveness. German tracking stations found no faults on their side. Launch conditions, gyro stability, and pulse jet thrust all appeared normal. Yet V-1 losses continued rising. By mid-July, the pattern was unmistakable. The British gun belt had moved into a performance range no Luftwaffe model had predicted. Inside Flak Regiment 155W, engineers compared every variable they could measure. None accounted for the increase. The missile hadn't changed, the defense had. For German command, the trend created a single operational warning. British guns were now achieving results that timed fuses should not be able to deliver. It was the first clear sign that a new, unidentified capability had entered the fight. As V-1 attacks intensified, British air defense planning shifted from incremental adjustments to structural redesign. The previous defense layout, distributed guns positioned inland, no longer matched the missile's flight profile. The V-1 moved too fast and crossed the coast too low for the older geometry to deliver consistent firing opportunities. A new approach took shape. Concentrate the gun belt along the south coast, place heavy batteries within direct line of sight of the Channel, and ensure every weapon had immediate radar support. This configuration compressed detection, tracking, and firing into a single, unified process. Less distance meant less time lost to calculation or misalignment. The most important change came from radar integration. SCR-584 sets, provided through US production, replaced earlier systems that struggled with fast, low-altitude targets. The new radar tracked automatically once locked. Operators no longer had to manually adjust for target drift. The radar fed data directly to the fire control computer. Predictor number 10 served as the second critical component. Its purpose was simple: convert radar tracking output into gun orders without delay. Trajectory, lead angle, fuse setting sequence, and elevation were computed in real time. This eliminated the long-standing timing gap that had limited British gunners since 1940. Another deliberate adjustment addressed security. By shifting the gun belt closer to the coastline, dud shells fell into the channel rather than populated areas. This tactical choice prevented German forces from recovering intact rounds for inspection, a vital precaution once new ammunition types entered service. Gun crews underwent revised training cycles to handle the increased rate of fire. The new system demanded precise coordination between radar operators, predictors, and battery commanders. Communication drills became as important as marksmanship. Every position in the chain had to execute without pause. Once fielded, the upgraded system demonstrated a clear pattern. Target detection occurred earlier. Tracking stabilized faster. Guns fired with shorter delays, and shells burst closer to the missile's flight path. Each improvement by itself offered only a small advantage. Combined, the upgrades created a tactical environment where the V-1 lost the margin it previously relied on. At this stage, the British defense structure still used mixed ammunition types, but the system itself was ready for a new kind of fuse, one designed to remove the need for perfect timing altogether. The architecture of the gun belt was in place. What remained was the introduction of an electronic component that allowed every near miss to behave like a direct hit. Before the V-1 campaign reached its peak, Allied laboratories had already completed a device that would overturn every German assumption about anti-aircraft warfare. Official documents masked it under the deliberately misleading code name VT, short for variable time. The term concealed its real nature. The fuse was not timed at all. It was a miniature sensing system, a self-contained electronic device that detonated automatically when its target came within range. For the first time in the history of heavy guns, a shell could think for itself. The technical principle was straightforward to describe. As the shell flew, the fuse would emit a continuous radio signal. When the reflected energy from a nearby aircraft, or, later, from a V-1 flying bomb, reached a certain threshold, the circuit would trigger detonation. But turning this principle into a functioning battlefield device required solving problems that engineers on every side of the war had long declared impossible. A fuse cavity was small, a gun's launch shock was violent, and the shell spun at more than 25,000 revolutions per minute as it left the barrel. Any electronics placed inside would need to survive all three conditions at once. German researchers had abandoned the idea early. Their prototypes burned out, misfired, or failed instantly under shock. The Luftwaffe Technical Office concluded the concept was operationally infeasible. They were wrong, because the Allies approached the problem differently. Most accounts of the VT fuse focus on its sensing circuit, the miniature radar inside the shell. But the circuit could not function without power, and providing that power proved almost as difficult as designing the sensor itself. Conventional batteries were useless. Stored for months, they would self-discharge. Exposed to the gun's setback shock of nearly 20,000 G, they shattered. Even if they survived firing, the intense spin often tore internal plates loose. Engineers needed a power source that could remain chemically inert for years, survive the gun's violence intact, and then activate only when the round was already in flight. What emerged from American ordnance laboratories looked nothing like a normal World War II battery. It was a reserve or sleeping battery, a small sealed cell containing separate chemical components. Only when the shell was fired, the instant the projectile experienced the crushing shock of acceleration, did an internal glass ampule break. The electrolyte flooded into the dry cell, completing the chemical path and bringing the battery to life in milliseconds. To anyone unfamiliar with the concept, it sounded absurd. A battery that stayed dead on the shelf but came alive during the most violent moment of its existence. Yet, it worked better than any conventional design. It provided steady current for the short duration the fuse needed to sense, think, and detonate. Without it, no miniature radar could survive long enough to function. The Germans had no equivalent. Their scientists had dismissed the idea as fantasy. Their industry could not mass-produce such components even if they had tried. With the battery solved, the rest of the design could finally function. Inside the nose of each shell sat a tiny oscillator, its vacuum tubes derived from hearing aid technology and ruggedized by Sylvania and Western Electric. This oscillator transmitted a continuous radio signal outward. As the shell approached a V-1, its metal fuselage reflected the signal back toward the fuse's antenna loop. A detector circuit only a few centimeters long, but stable enough to operate inside a spinning projectile, measured the change in reflected energy. When the amplitude crossed a preset threshold, the fuse triggered the detonator, exploding the shell at precisely the distance where its fragmentation pattern was most lethal. Unlike timed fuses, there were no settings to adjust, no predictor errors to compensate for, no best guess calculations from a gun crew. The fuse simply waited until physics said, now. Because the fuse contained sensitive electronics, early use remained tightly controlled. Over the Pacific Ocean, dud rounds sank into deep water, safely out of enemy hands. Over the European mainland, that was impossible. Only when the British reconfigured their defensive gun belt along the south coast, ensuring that dud shells would fall into the channel, did Allied command authorize the fuse for the V-1 campaign. By mid-1944, every element of the British defense finally came together. SCR-584 radar could now track each incoming V-1 with a level of precision no earlier system had achieved. Predictor number 10 took that radar data and turned it into firing orders in real time, eliminating the delays that had limited timed fuse gunnery since the start of the war. Coastal gun crews, drilled day after day, executed these orders almost automatically, creating a firing rhythm that matched the missile's speed. And at the center of this new system was the smallest component of all, a reserve battery hidden inside the fuse, powering the miniature sensing circuit Germany believed could not exist. As soon as VT-fused ammunition entered the British stocks, the effect became unmistakable. Engagement reports shifted from scattered successes to consistent, repeatable kills. V-1s that once survived dozens of near misses now broke apart when shells burst just close enough. The difference was not in the gun accuracy, not in the radar, not in British timing or drills. It was in the fuse, and in the one-shot battery that allowed the fuse to function at all. Within days, the interception percentage rose so sharply that German analysts suspected sabotage or statistical error. They rebuilt their tables, rechecked launch logs, verified predictor models. Each morning, the same impossible figure appeared. By the final week of August, British coastal batteries destroyed 82% of all V-1s crossing their sectors. On paper, the V-1 remained a fast, evasive, statistically resilient weapon. In the real world, a palm-sized battery had quietly rewritten the battle. Before the proximity fuse ever reached the British gun belt, its core technology had already survived a far more punishing battleground, the American engineering process that created it. The fuse was not the work of a lone inventor but the result of a coordinated national effort, centered at the Johns Hopkins Applied Physics Laboratory, under physicist Dr. Merle Tuve, the man who refused to accept the global belief that proximity fuses were impossible. Tuve attacked the problem from a direction no other nation had attempted. Instead of refining mechanical timing, he reframed everything as an electronics challenge. If a shell could carry its own miniature radar, stable inside a spinning projectile and simple enough to mass produce, then gunners no longer needed perfect timing. The shell would detonate when physics demanded, not when crews hoped. To do this, Tuve assembled a team of exceptional young engineers and scientists. Robert Page, a pioneer of early radar, helped compress transmitter, receiver circuitry into a form that could survive launch shock without losing signal coherence. Working beside him was James Van Allen, years before the radiation belts that would bear his name, conducting brutal live fire trials, building test packages, and identifying which prototypes survived the gun's acceleration and which ones didn't. But all of their designs depended on a single unconventional idea, a power source that could stay inert on the shelf, survive firing, and activate only after the shell was already in flight. That strange one-shot battery, introduced in the previous section, became the keystone that allowed the entire sensing circuit to function. Industry partners filled in the rest. Sylvania and Western Electric ruggedized miniature vacuum tubes originally designed for hearing aids, reinforcing them to endure shock levels no civilian device had ever experienced. Prototype batches were fired from naval guns, dug out of sandbanks, torn open, catalogued, revised, and fired again. Improvements appeared in days rather than months. A pace Axis industry, with its artisanal production lines, could not dream of matching. By late 1942, APL had delivered what military planners desperately needed: a compact, ruggedized radio fuse that transmitted continuously, sensed reflected energy, and detonated the moment a target entered its lethal radius. APL solved the physics. American industry solved the manufacturing. The Navy Bureau of Ordnance deployed the first rounds in the Pacific in early 1943, where they proved themselves instantly. By the time the V-1 campaign began, the United States was producing proximity fuses at a scale the Luftwaffe could not imagine. Behind that industrial tide was TÜV's breakthrough team, Page, Van Allen, and thousands of technicians, whose work transformed a theoretical curiosity into the decisive element of the British coastal defense. It was the breakthrough the V-1 campaign had no answer for. While British gunners were discovering the full power of their new ammunition, German intelligence units were trapped inside a framework they had built long before the V-1 campaign even began. Their analysts watched the results, recorded the losses, and plotted the trends, yet every piece of data they gathered pointed back to an explanation that no one inside the Luftwaffe Technical Service was willing to consider. The first reports came from coastal observers. They noted that British flak bursts were landing unusually close to the missiles, but the patterns didn't resemble improved timing. The spacing was too consistent. The detonations were too well placed. Trained eyes could tell when a burst was lucky. These were not lucky. These were controlled. Signals units searched for hints in British radio traffic, new radar procedures, unusual fire control chatter, anything to indicate a shift in tactics. Nothing appeared. The British spoke the same way they always had. Whatever had changed was happening inside the shell, not outside the gun. Recovery teams combed the French coastline for fragments of British rounds. Most shells detonated over the channel, exactly where Britain intended them to fall. A few broken casings reached shore, but the vital components, the electronics, never survived. What the Germans recovered looked like ordinary steel shrapnel, indistinguishable from any other anti-aircraft round. They searched for mechanical clues, unaware they were hunting a device that left none. Inside the Luftwaffe technical office, analysts rebuilt their models again and again. Radar improvements, possibly. Better predictor handling, likely. A sudden leap to 80+% interception? Impossible. Every explanation they allowed themselves stayed within the boundaries of what they believed technically achievable, and inside those boundaries, nothing fit. The greatest barrier wasn't lack of evidence. It was doctrine. Years earlier, German laboratories had attempted their own proximity fuse concepts. The designs overloaded, misfired, or tore themselves apart under launch shock. After dozens of failures, researchers concluded the entire idea was unworkable. A fuse containing electronics small enough, stable enough, and durable enough to function inside a spinning shell was dismissed as fantasy. Once that belief hardened, every later field report was filtered through it. So when British shells detonated near V-1s with lethal consistency, German analysts explained it away as improved timing. When multiple bursts destroyed a missile without a visible direct hit, they attributed it to refined predictors. Even when entire salvos vanished in mid-air, the conclusion remained the same. British crews had somehow become extraordinarily efficient. The closest Germany ever came to discovering the truth occurred months later, during the Ardennes offensive. Troops overran an American ammunition depot and found crates filled with proximity fuses. The devices were sealed, unfamiliar, and marked with coded labels that revealed nothing. To German ordnance officers, they looked like complex variants of timed fuses. No one disassembled them. No one recognized the internal components. The most advanced anti-aircraft fuse of the war sat in their hands and passed through unnoticed. By the time the V-1 losses became catastrophic, the blind spot inside German intelligence was complete. They saw the effects of the new fuse every morning in their interception tables, yet the cause remained invisible. They never imagined electronics small enough to serve as a radar. They never imagined a power source designed to awaken only after firing. And because they could not imagine those things, they dismissed them long before the first V-1 crossed the channel. The result was not simply an intelligence failure. It was a failure of imagination, and it left the V-1 campaign defenseless against a technology Germany no longer believed could exist. By late August, the British gun belt reached a level of performance that exceeded every prior projection. Radar crews, predictors, and gun teams were now operating as a single coordinated system. The introduction of VT-fused ammunition turned that system from a defensive line into a precision engagement network. During this period, interception results showed a sharp upward break. V-1s crossing the coastline faced overlapping radar coverage and tightly sequenced fire orders. Shells no longer depended on perfect timing. They only needed to pass within sensing range of the missile. In most engagements, that window proved sufficient. Operational reports recorded a surge in confirmed kills. The pattern stayed consistent over several days, removing the possibility of statistical fluctuation. On the highest performing day, the gun belt neutralized more than 4/5 of all incoming missiles. That figure expanded beyond tactical success. It signaled a strategic shift. German launch crews attempted multiple adjustments. Some salvos fired at slightly altered altitudes. Other waves departed at staggered intervals in hopes of saturating British defenses. Night operations increased. None of these variations produced meaningful changes in survivability. Analysis units at Flak Regiment 155W confronted the same conclusion each morning. The British response had outpaced the missile's ability to adapt. Flight paths remained predictable. Pulsajet thrust levels did not change. The V-1's design offered no room for evasive maneuver or countermeasure. British records from the coastal batteries showed a parallel view. Radar locks remained stable. Predictor solutions stayed inside acceptable error margins. Gun crews executed firing sequences with minimal delay. The VT fuse compensated for any residual variation. The V-1 campaign needed volume to offset attrition. Once losses passed a certain threshold, the weapon could no longer generate the pressure required for strategic effect. That threshold was breached in August. The missile's penetration rate fell too low to influence the broader air campaign. In effect, the V-1 offensive lost momentum while still in operation. Launch sites continued firing, but outcome profiles no longer aligned with German planning assumptions. The system had met a defense architecture it was never designed to defeat. By the end of the month, the operational value of the ground-launched V-1 had dropped below sustainable levels. The weapon still reached London, but not in numbers capable of reshaping Allied strategy. The decisive factor was not a single improvement. It was the cumulative effect of radar coordination, firing geometry, and an electronic fuse Germany never accounted for. While the V-1 campaign unfolded in Western Europe, a different contest played out in Allied and Axis factories. The effectiveness of the VT fuse depended not only on engineering but on the ability to manufacture it at scale. On that front, the imbalance between the two sides was decisive. American production lines built for radios, household appliances, and commercial electronics shifted rapidly to wartime output. Companies such as Crosley, Sylvania, and Western Electric repurposed existing assembly tools to mass-produce miniature components. As techniques improved, unit cost dropped sharply. By early 1945, a single VT fuse cost only a fraction of its original price. The numbers illustrate the gap. US factories produced tens of millions of vacuum tubes each month and fed them into fuse assembly lines running around the clock. Daily output reached 40,000 finished fuses. Every shipment supplied British batteries with consistent, reliable ammunition. German industry followed a different model. Weapons programs often relied on small workshops, manual assembly, and precision processes executed by limited teams. Scaling a new device required tooling changes, trained specialists, and stable raw material access, conditions Germany increasingly lacked. Air raids, resource shortages, and forced labor dependence slowed production and reduced quality control. The V-1 program reflected those constraints. Each missile required extensive labor, tight tolerances, and supply chains that ran through occupied territory. Output never approached the volume needed to offset rising losses. Even at maximum effort, total ground-launched V-1 production remained far below the rate at which Allied factories produced proximity fuses. A comparison of monthly production tells the story plainly. American proximity fuse output in a single month exceeded the total number of V-1s built during the entire war. This mismatch made the long-term viability of the V-1 campaign mathematically unsustainable. Every improvement in British defense reduced the missile's impact, while Allied ammunition supplies continued to expand. Industrial flexibility offered another advantage. American companies could modify designs, test new components, and integrate upgrades without interrupting delivery schedules. German workshops lacked that margin. Any change risked slowing production or disrupting already strained logistics. By the summer of 1944, the operational balance had already shifted. The V-1 remained a functioning weapon, but its strategic value depended on volume. Once attrition rose beyond the point that German factories could cover, the missile no longer represented a scalable threat. The disparity was not accidental. It grew from two different wartime economies, one optimized for mass production, the other constrained by manual processes and diminishing resources. When the VT fuse entered British service in significant numbers, that asymmetry became a battlefield outcome rather than an industrial statistic. When the V-1 offensive began to lose momentum, German planners assumed the decline came from British procedural refinement. That assessment held until the war ended. Only after surrender did the Luftwaffe's technical community learn what had actually happened. Interrogation teams from the United States and Britain presented captured VT fuses to former weapons engineers. Initial confusion shifted to disbelief as they inspected the rugged miniature tubes, shock-resistant wiring, and compact circuitry. The components contradicted every conclusion drawn from their own failed pre-war prototypes. What they had dismissed as physically impossible had been operating inside every British anti-aircraft shell. Officers who had monitored the V-1 campaign now recognized the pattern they had never been able to explain. Near-miss detonations were not timing miracles. They were the product of an onboard sensor the Germans had removed from their threat models years earlier. Because German research institutes abandoned proximity fuse development early in the war, analysts never considered it a plausible British capability. Any field report hinting at such a system was reinterpreted as improved training or better fire control discipline. Captured production summaries revealed the second shock. Allied factories had manufactured millions of fuses and distributed them across multiple theaters. Each unit cost far less than a single V-1 missile. The volume alone explained why Britain could maintain high interception rates while Germany struggled to sustain offensive output. For British officers who oversaw London's defence, the post-war review confirmed the necessity of their earlier security restrictions. VT ammunition had been withheld from most ground operations to prevent capture, delaying its broader use in Europe. But the decision to employ it against the V-1 was validated. Dud rounds falling offshore kept the technology out of German hands. As wartime secrets became public, the proximity fuse emerged as one of the conflict's most influential force multipliers. It upgraded existing guns, ships, and artillery units without requiring new platforms. Its impact spread across every theater where it was deployed. For Germany, the revelation closed a chapter defined by technical overconfidence and incomplete intelligence. The V-1 offensive had been built on assumptions that no longer matched battlefield reality. Once engineers understood the true nature of British ammunition, the scale of the miscalculation became clear. They had faced a defense built around a device they believed could not exist. The VT fuse did not end the war, but it prevented the V-1 from becoming a decisive weapon. In the months after surrender, German scientists acknowledged a gap they could not have closed, one rooted as much in industrial capacity as in innovation. The full impact of the VT fuse became clear only after British records were consolidated. Civilian losses from V-1 strikes were far lower than early projections, and commanders estimated that the fuse had prevented thousands of deaths during the summer of 1944. Artillery data told the same story. Before proximity fuses, each V-1 kill required heavy ammunition expenditure and near-perfect timing. With VT rounds, the number of shells per kill dropped sharply. What had been a probabilistic system became a reliable one. The fuse's influence spread beyond Britain. In the Pacific, U.S. naval forces employed VT ammunition against low-flying aircraft with decisive effect. Carrier groups reported fewer successful enemy attacks, and commanders credited the fuse with reducing ship losses in major operations. Post-war analysis confirmed that the technology marked a shift in military design. Instead of creating entirely new weapons, the Allies enhanced existing guns with electronics that multiplied performance across every unit that used them. Captured German scientists later admitted they had misjudged the potential of miniaturized components, and that their industrial system could not have produced such a device at scale. By the end of the war, the VT fuse stood out as one of the few technologies that delivered immediate, measurable results across multiple theaters. Its value came not from complexity, but from how effectively it transformed near misses into kills and reshaped the balance between offense and defense.